You know about this. Any more notes? Now, more on fundamental aspects of thermodynamics. We finished last time by my asking you to take a look at the thermodynamic properties information for carbon graphite and carbon diamond. Point. Carbon graphite is standard state carbon. It's the most thermodynamically stable form of carbon. Do you not find that interesting? Given that, for example, you know, diamond is a much tougher, harder material than carbon graphite. Nevertheless, if you look at the data in the thermodynamics property table, you'll see that forming carbon diamond from carbon graphite is associated with a delta H0 value that's positive. Endothermic bond weakening. Bond weakening. Conclusion? Carbon-carbon covalent bonds in graphite versus carbon-carbon covalent bonds in diamond. Which are stronger? The ones in graphite. Then why is graphite the softer material? Take a look at the other thermodynamic properties data point. The standard molar entropy of carbon graphite is greater than the standard molar entropy of carbon diamond. Why is this? How can the material with the stronger bonds have the higher entropy? Have a greater capability to distribute internal energy? And wind up having a lattice which from an overall lattice strength standpoint is weaker. Let's take a look. Regarding bond strengths, here is an abbreviated Lewis structure for a carbon atom in the graphite lattice. Each carbon atom in the graphite lattice is covalently connected to 1, 2, 3 nearest neighbor carbon atoms. Here's a model. To see this bond structure that I've sketched on the board, I'll hold a model like this. Look, for example, at this carbon atom as a reference atom. The atoms in the model are alternatively colored to make visualization easier. You see that this carbon atom that I'm pointing at is covalently connected to this carbon, and this carbon? However, in the diamond lattice, each carbon atom is covalently connected to 4 nearest neighbor carbons. sp3 hybridization for this carbon versus sp2 hybridization for any carbon atom in the graphite lattice. Diamond model. This is not so easy to see because some of the atoms that you have to look at are inside the model, so to speak. If I point at this carbon atom is covalently connected to this carbon atom and this carbon atom and this carbon atom and this carbon atom right over there. But notice that the covalent bonds per carbon atom in the diamond lattice extend in a 3-dimensional tetrahedral pattern, whereas the covalent bonds for carbon atoms in a graphite lattice do not extend 3-dimensionally. They extend 2-dimensionally. Did you not learn in Chemistry 2045 that sp2 hybridization is associated with what kind of geometry? What kind of geometry? 3-dimensional or planar? Planar. Trigonal planar, specifically. Because these bond angles are all 120 degrees, whereas these bond angles are all perfectly 109.45 degrees, the perfect tetrahedral angle. Because in the pure diamond lattice, there's nothing but carbon atoms. Well then, this accounts for why carbon-carbon covalent bonds are stronger in graphite than they are in diamond. Here. What's carbon-carbon bond order? Diamond. Carbon-carbon bond order. You remember what bond order is, don't you, from 2045? 1. What's the carbon-carbon bond order in graphite? 4/3. Carbon, 1, 2, 3 bond sites. And at these 1, 2, 3 identical bond sites, how many covalent bonds? 1, 2, 3, 4. Is there actually a double bond between any carbon atoms in graphite? Are there actually any single bonds between carbon atoms in graphite? Now, what property does this thing really have that unfortunately cannot be accurately represented by drawing pictures? It's called resonance. Well, this will remind you, regarding associated properties, that graphite is a thermal conductor as well as an electrical conductor throughout a plane of carbon atoms. But throughout the lattice, no. This thing doesn't conduct this way, but it conducts this way. These are the carbon atoms connected to each other in a plane with this property called resonance. It's like mobile pi electrons. Diamond. Now, diamond is an electrical insulator. But thermally, this is one of the best heat conductors known. Is that surprising? Well, I don't know if you talked about this in 2045, and I don't know that I have a real sharp and clear story to tell you about this. But since all carbon atoms are connected to each other by formal covalent bonds, when you pop thermal energy into this thing, what's its ability to vibrate? Almost nothing. These atoms are locked in this tight lattice. Rotate, nothing. It's solid state. Translate, nothing. So when you pop energy into this lattice, it passes right through. Marvelous thermal conductor. Not nearly so for graphite. Electrical conductor this way, thermal conductor this way. But thermal conductor, electrical conductor this way? Because if you pop energy into a graphite lattice that's oriented like this, and you pop the energy in here or pop the energy in here, you've got a lot of wiggling that can take place between these planes of carbon atoms. Anybody writing notes with a graphite pencil? What would happen if you were writing your notes with a diamond pencil? Your notes would be a series of scratches through the paper or on the desktop. When you write notes with a graphite pencil, which some of you are doing right now, and leave behind this smear of carbon atoms, have you broken carbon-carbon bonds when you wrote your notes?
No.
Absolutely not. What did you do? You separated these weak these planes of atoms from each other, because the planes of atoms are connected by these very weak attraction force interactions known as London forces, and that's it. That's why this has the higher entropy, because these planes are connected by these weak association forces, London forces only. And we've pointed out already why the carbon-carbon bonds are stronger. That's why this stuff has a lower enthalpy, because it's got the stronger carbon-carbon bonds, but the higher entropy, because the planes of atoms are connected by these weak London forces. Very low entropy, relatively speaking. Because the rigid three-dimensional covalent lattice, which extends throughout, that's essentially non-budgeable when you input thermal energy. Upshot? Marvelous thermal conductor. lousy electrical conductor because you can't get electrons to mobilize between any carbon-carbon bond site in the diamond lattice to another carbon-carbon bond site. Oh, I haven't fixed that damn thing yet. Now we go to a section which you jumped over yesterday in discussion class, because I think it's easier for me to present this consideration here. If for no other reason, because I have this. A sample of stuff contained in a sealed flask. Never mind the kind of whitish appearance, that's because of my chalk-smeared hands. Experiment. We imagine we take a piston cylinder apparatus, and at 25 centigrade, 1 atmosphere total external pressure, we contain within 1 mole pure N2O4 gas. Simultaneously, in a second piston cylinder gadget, we contain 2 moles NO2 gas at a total pressure of 1 atmosphere. So we know that if these gases obey the ideal gas law, PV equals nRT, which they do practically speaking, then the volume of this cylinder is twice the volume of this cylinder. Tell me, for this cylinder, if we're able to do this experiment, about what volume would be observed inside this piston cylinder? Would we have to have a big piston cylinder to do this? How big would it be? How many? How big? How big? 22.4 liters? Bigger than that. Remember, 22.4 liters is the volume occupied by 1 mole of a gas whose behavior is describable by PV equals nRT. Provided that the sample is at what temperature? 0 centigrade. We're at 25 centigrade. And what do gases do when you warm them up? Provided that they're contained in a device like this where the volume is variable. What do gases do when you warm them up? They expand. So if I know the volume is 22.4 liters at 0 centigrade, how will you figure out the volume at 25 centigrade? What are you going to do, Boyle? What are you going to do, Charles? You remember these people? Yeah. You talked about their laws in 2045, didn't you? Well, now let's put them to use. The law with which we are immediately concerned is Charles' law. Yeah. Volume occupied is directly proportional to temperature. You know the volume is 22.4 liters per mole at 0 centigrade. How will you calculate the volume at 25 centigrade? Because if you tell me something about V1, T1 and V2, T2 or any of that stuff, I reject that. Is that the way you did it in 2045? I reject that. I want this stuff to be understood. Did you learn in 2045 that PV equals nRT, this equation of state is an energy equation? Did you learn that? It shows you interconversion between mechanical energy and thermal energy. More on that later. But all I'm going to do, if I want to know this new volume, is to write this, which I know to be the volume occupied by the mole of the ideal gas at what temperature? And what is 0 centigrade in Kelvin? And we are now considering the same sample of gas, 1 mole, at how much Kelvin? 298. Well, tell me, do I multiply this volume by 273 over 298 or 298 over 273?
The second one.
Which one?
Second. 298.
298 over 273, because that corresponds to an increase in volume. That's all there is to it. You recognize this damn stuff when you warm it up, it expands. And the hell with this V1, T1 junk, because that's not understanding. So you do the arithmetic, you'll find out you got a volume here of about 25 liters. So for this gadget, we got a volume that's about 50 liters. It's a little bit less. We need big devices if we want to do this. Now the question that really I'm concerned in having you answer is whether or not I can actually do this experiment. Because if I'm going to do this experiment, I got to be able to contain a mole of pure N2O4 and 2 moles of pure NO2. So here's our continuation of this experiment. We imagine to create this setup, this setup. We seal each. Let's stand for a good long time. A good long time so that we shall overcome any kinetic barrier that might stand in the way of our results. And while we're waiting, we take a look at this reaction equation and apply to it the data that we find in Table 1, the thermodynamic properties data table at the end of Chapter 21. At the end of Chapter 20, if you look up the standard free energy of formation of N2O4, cited at 298 K, because that's what it's cited at in this table, and the standard free energy of formation for NO2 and multiply it by 2 and apply Hess's law, you find out for this reaction is written delta G0, because it's based on standard free energy values, standard free energy of formation values, is minus 4.7 kilojoules. What's this tell us? Reaction spontaneous. Does it tell us something about the relative thermodynamic stabilities of a mole of this versus 2 moles of this at these conditions? Which one is more stable? Is this spontaneous going this way? Yes. So which one is thermodynamically more stable? 1 mole this, 2 moles this. 1 mole this. So back to the experiment. We now have waited this infinite period of time. We open each piston cylinder gadget and we analyze the contents of each. What do we find? If I observe these piston cylinder gadgets while we were waiting this infinite period of time, would this internal volume remain the same? Would this internal volume remain the same? Would one internal volume change while the other internal volume remain the same? Or would both internal volumes change? What would we see?
One changes, the other stays the same.
I got a vote for one changes and the other stays the same. How many agree with that vote? How many agree that neither volume will change? How many agree that both volumes will change? I saw one. Oh, there's a half a vote. There's another half a vote. Well, there's another half a vote. Put your hand like this is a full vote. Like this is a half a vote. Okay. All right, then I'll count those as full votes. We got 5 correct votes. Both volumes change. Why do both volumes change? Because the most stable thermodynamic state a system can exist in is called what?
Equilibrium.
Equilibrium. And under no circumstances, if you start with pure this, will you decompose entirely into pure that? Under no circumstances, if you start with pure this, will it combine to make pure this? Instead, you get the most stable thermodynamic state for the system, called equilibrium. How about that? So let's take a look at this graph. A G-state graph. It's not drawn to scale, but it's drawn so as to at least give us an idea what's going on from a change in free energy standpoint. 1 mole of N2O4, 2 moles of NO2. We're at P total equals 1 atmosphere and 298 K. The data we wrote over there for our reaction tells us that if I go from 2 moles of NO2 to 1 mole of N2O4, I go this way, minus 4.7 kilojoules of energy is made available for me to do usable work. That's why it's called free energy. It's available for work. On the other hand, if I want a mole of this to fall apart and become 2 moles of this, then the change in free energy is plus 4.7 kilojoules. Just depends on which way we go. Okay? But we don't observe either change in free energy in either cell system, in either cylinder. Instead, we find out that if we start with the 1 mole of N2O4, as we imagine to do in this cylinder, about 20% of it dissociates and becomes NO2 molecules. And that's where the system stops, because now it's at equilibrium. On the other hand, if I start with 2 moles of this, because we did realize that the tendency for this to convert to this is spontaneous, but not for complete conversion. And pardon me, that's also spontaneous. But the tendency for 2 moles of this to combine and become this, and some of this remaining, so that we have the equilibrium mixture. That's the greatest tendency we have. And here's what we get. Here is EQ. Now take note. If you go from a mole of this to 2 moles of this, that's anti-spontaneous, isn't it? That's plus 4.7. But if I go from 1 mole of this to this, the G state got lower, didn't it? That's a favorable change in free energy, spontaneous. And if I start with 2 moles of this, I don't wind up going to 1 mole of this. I wind up going to this system, which is the equilibrium system, where most of these, but not all of these, have converted to N2O4 molecules. Because notice that the change in free energy going from here to here is greater than the change in free energy going from here to here. Isn't it? Here's what I get if 2 moles of this becomes a mole of this. But if 2 moles of this becomes equilibrium, I'm doing better. And that's the way it's going to go. Because that's the most stable energy change this thing can show. And why does it do this? Because it gets to the most stable thermodynamic condition any system can be in. Equilibrium. So, as we said, or at least intimated, if I could do this experiment, this volume would increase till I get to the equilibrium mixture. This volume would decrease till I get to the equilibrium mixture. And the volumes inside would be the same. Never mind my lousy sketches. So I ask this question. On your paper right now, draw a Lewis structure for NO2. On your paper right now, draw a Lewis structure for NO2. And then draw a Lewis structure for N2O4. Draw them both right now. Time's up. Time's up. That's it. If you've acted on this correctly, you will come up with two Lewis structures. This one or this one. Now notice that for this Lewis structure, or this oxygen atom has an unpaired electron, because the total valence electron count for NO2 is how many? 17. So it's got to have at least one half-filled orbital. It's got to be something which chemists call a free radical. Radical is a term which chemists apply to species which have one or more half-filled orbitals in their valence structure. One or more unpaired electrons. Did you learn anything in Chemistry 2045 about the reactivity of radicals compared to non-radicals? Did you recognize in Chemistry 2045 that damn near all stable chemical species are species which have a total number of valence electrons which is an even number because they don't have any half-filled orbitals? I'm curious, did you learn that? Yes. Well then, from that information, what would you conclude to be more stable? The radical or the non-radical? The non-radical. Correct. Which accounts for the natural tendency of NO2 molecules to convert to N2O4 molecules, because you're converting radicals to non-radicals. NO2, radicals. N2O4, non-radicals. Now then, which of these Lewis structures do you prefer? And why? Notice for this Lewis structure, zero formal charge distribution. But for this Lewis structure, this oxygen atom has got a formal charge of -1 and the central nitrogen atom got a formal charge of +1. But it's not a violation because these are oppositely charged, opposite sign formal charges, and they're on adjacent atoms. So Coulomb likes that because the plus-minus charges are next to each other. They can't get any closer than being next to each other. What Coulomb doesn't like is if you write a Lewis structure and you got plus-minus formal charge separated by one or more intermediate atoms with zero formal charge. Coulomb says, I don't like that. Which of these Lewis structures do you like better, and why? Like this one better? Yeah. Why?
Because the oxygen has a negative charge, and since it has a higher electronegativity.
Never mind the negative charge. Do you see that? The main difference between these Lewis structures is that for this Lewis structure we have an oxygen atom that's deficient of octet. For this Lewis structure we have a nitrogen atom that's deficient of octet, each by one electron. Which atom do you think will be more stable with the valence electron environment division by one electron from octet? Oxygen or nitrogen? Which one will be more stable? Nitrogen. Why? Because nitrogen has a blah blah compared to oxygen. Look, lower electronegativity. That's right. You betcha. You betcha. Which dictates why. The correct Lewis structure for NO2 is this. Now tell me, since we've argued that it's the experimentally verifiable fact which is the only dictator in science, if this is true, when NO2 molecules get together with each other to become N2O4 molecules, what bond are we making? What bond are we making? Notice that if each of these Lewis structures were acceptable, if sometimes an oxygen atom had the unpaired electron, and sometimes the nitrogen atom had the unpaired electron, when NO2 molecules got together with each other to make N2O4, sometimes you'd make an NO bond, sometimes you'd make an OO bond, and sometimes you'd make an NN bond. Ha-ha! But our argument says the only Lewis structure which really makes sense is the one with the unpaired electron and nitrogen. So I repeat my question. When NO2 molecules react with each other to become N2O4 molecules, what bond do you make? NN. And guess what? When we look at the Lewis structure, when we go to the lab and look at the true structure for this stuff, that's what we get. NN bond forms. And there's no NN bond, and the original NO2 molecules can't be. Interesting, isn't it? Now another question. What have we got in this flask? Did you recognize in Chemistry 2045 that these radicals often have, since their valence electron structure is not as stable as the non-radicals, these radicals often have a valence electron structure which is excitable by electromagnetic radiation in the visible region of the spectrum. You know, white light. And when white light interacts with electrons on species, what do we see? It's called color. Do we see any color in here? Goody. What do you think we're looking at? What do you think this brown stuff is? What is it? It's NO2! Question. We now know that NO2 is in this flask. Do you think it's the only stuff in this flask? No. Not if you believe our analysis. In fact, since we're at 298 K, practically speaking, in this room, I recognize that in this flask, although you can't see it, most of the gas that's in here is what? N2O4, which is colorless. How about that? Now, one more question. We recognize that for this conversion, 2 moles of this becoming 1 mole of this, which is spontaneous, is this transformation driven by delta H0, delta S0, or both? Clearly it's got to be driven by at least one of these because this thing is spontaneous. Which means at least one of these terms has got to be responsible for this reaction being spontaneous. Delta H0, delta S0, or both. 3 possibilities exist. Well, let's open the voting booth again, since we're very much in the vicinity of election time. Hand up if you vote for both. Hand up if you vote for delta H0 only. Hand up if you vote for delta S0 only. My golly, we got votes all over the damn place. I don't know who's going to get elected. Remember the Lewis structure analysis we just made? Remember recognizing that a reaction is guaranteed to be exothermic if bond improvement takes place? Regarding bonds, what happens when this reaction runs? Are we breaking any bonds? Not at all. The only thing that's happening from a bond standpoint when this reaction runs is bond formation, isn't it? What does that tell you? This reaction is associated exclusively with bond formation. Does that or does that not guarantee that it's exo? Guarantees exo, you betcha. Now you tell me. Here's entropy, looking at this system. It says here, I got 2 moles of gas at this temperature and pressure. But now, because I made a bond, I only got 1 mole of gas. Entropy says, I hate that. If entropy had its way, if entropy was the only force existing in nature, there would be no bonds, there would be no solids, there would be no liquids, there'd be no people, there'd be no buildings, there'd be no chairs, there'd be no atoms, there'd be nothing stuck together. Nothing. This giant mess of vapor phase nothing. Ha! But if enthalpy is the only force in nature, the only force in nature, we'll have this big rock with bonds of infinite strength. There'll be no motion, no gas, no liquid, no vibrational freedom, no rotational freedom, no translational freedom, no Big Bang, no nothing. So do you think, as we observe nature, we recognize it to be a fight between entropy and enthalpy? And where does this fight wind up? Where does it wind up? At equilibrium. All the time. How about that? Isn't it cute? Now, some of you talked about this yesterday, some of you did not. We'll finish with this consideration today. You know about conditions to be established to do standard state studies on transformations involving pure substances. Standard state. Pure liquids, pure solids by definition in the standard state, and for a solution we'll take the solvent to be in the standard state because it is by far the principal component of the solution, so it's rather like pure liquid. Solute species 1 molar. Each gas component above the system, because gases are less dense than solids and liquids, at partial pressures of 1 atmosphere each, or 1 bar. But what do we do if I want to do standard state studies on reactions in solutions which involve ions? Because I don't have an absolute reference point anymore. The third law gives us an absolute reference point for thermodynamic considerations applied to pure substances. Third law. The entropy of a pure crystal, perfect crystal, for a pure substance at 0 Kelvin is 0. But how could I possibly do solution studies at 0 Kelvin? Because when I take a solution and try to cool it to get it to 0 Kelvin, what happens to the solution? What does it do? Well, it freezes occurs, okay? Now tell me, are you all familiar with popsicles? Yes. I like popsicles too. Okay? Is a popsicle a solution or a suspension? Suspension. It is a suspension. Because when you freeze your soda pop dissolved in water, or your Kool-Aid dissolved in water, you wind up with solute particles separating from solvent particles. You have a suspension of the flavoring agents and the agents which give this popsicle color suspended in this solid lattice of ice. Point? I don't have a thermodynamic reference point for solutions because solutions fall apart when I cool them off. As soon as the solvent starts to crystallize, the solution starts to disappear. So I got to define a reference point. The defined reference point is H+, aqueous, at a pH of exactly 0.00000 forever. 1 molar H+. So take note. Here's that reaction showing you the formation of H+. From the required molar quantity of the most stable allotrope for elemental hydrogen, which I define for this reaction. I define the change in free energy to be 0, the change in enthalpy under standard conditions 0, entropy to be 0, and the change in entropy for this reaction under standard conditions to be 0. There's my thermodynamic reference point. It's an arbitrary reference point. Do you see why it's arbitrary? You see why these are defined values rather than real values? Can I run this reaction? Can I go to the hardware store and get my bottle of electrons? No. But I can run this reaction next to other reactions, and we're going to look at this in detail when we get to the chapter on electrochemistry, because we'll recognize that this is not really a complete reaction. It's called a half reaction. It shows electron liberation. And next to this, we'll have to run another reaction which corresponds to electron consumption. Then we got a complete reaction. And so when we measured the change in free energy for this total reaction and half for this half set at 0, the measured change in free energy is for the other half reaction. One more question based on these definitions. Because we know that in water, there's no such a thing as H+ floating around. At the minimum, it's hydronium ion. So here's a reaction showing the conversion of H+ to hydronium ion. What's the change in free energy under standard conditions for this reaction? What's it equal to? 0. Because when I add this to water, am I changing the free energy of water? Am I changing the entropy of water? Am I changing the enthalpy of water? No. Because of these definitions. That means the standard free energy of formation for water, liquid, and hydronium ion compare how? They are equal. We'll pick it up from this point next time.